Talking about motion in a single dimension, we've already recognized that whether it's displacement or velocity or acceleration, we can just add and subtract vector values. So if I had something like 8 meters per second and then something like 3 meters per second, we know that if this is like a train and someone walking on the train, we can add those values to get 11 meters per second. Likewise, if we had that train moving at 8 meters per second and someone walking on it going back the other direction at 3 meters per second, we know that we would then subtract those values because a vector can be negative, and we would wind up with a 5 meter per second resultant vector. Well, when we start talking about vector addition in 2 dimensions, it really is still following the same idea. We're still going to draw these out as arrows representing the individual values, but now we're just going to connect them in multiple dimensions. So here I'm going to have my 8 meter per second vector, and here I'm going to connect my 3 meter per second vector, and my total is not 11 meters per second, but rather how much? Whatever the diagonal is going to be, right? So my resultant here is simply going to be 8 squared plus 3 squared equals c squared, Pythagorean theorem. So the square root of 73. Square root of 73. So my displacement, no, I can't just add it directly. I do have to treat it as a right triangle, finding the straight line distance between these two. The other piece that I would need here in order to properly identify this new resultant value or this new vector would be some kind of angle to tell me at what angle is this velocity moving. So to do that, I'm going to need a trig function. So in this case, I'm just going to use the tangent of theta is equal to opposite 3 over adjacent 8. So the inverse tangent of 3 over 8, which is inverse tangent of 3 over 8, I get 20.6 degrees. So at some point in your math courses, you've all done this. You've all taken values of lengths, added them together to get right triangles, broken right triangles down into angles and different sides. So there's nothing new here. What's going to be new is how we're applying it to moving objects. So in this case, sure, it was 8 meters per second and 3 meters per second. We're talking about a velocity, but what kind of specific object could we be talking about? Well, we could be talking about, say, sure, we could talk about a person still walking on a train. They're moving down, or the train's moving forward while they're moving across the seats. We could also talk about a boat and moving in a river, or we could talk about a plane flying in wind. All of these different types of motion involve more than one cause for motion, and therefore have to have the velocities or displacements added as vectors. A couple of terms that I've been using, component and resultant vectors. Anytime we add vectors together, component vectors are the individual pieces, and the resultant is what the components add to. So component vectors add to a resultant vector. So far, so good. Just a review of math. All right, well, let's go ahead and just take a look at how this would actually apply to a physics scenario, where we've got a river that's flowing at, let's say, 6 meters per second. Navigating that river is some guy paddling a boat, and we'll go ahead and put oars on our boat. And he's going to paddle the boat at 9 meters per second, which is rather quick for a boat that's man-powered. Okay? If our river is 40 meters across, how far downstream will the boat hit the opposite bank? how far downstream will the boat reach the opposite side? Okay. So first of all, if we were standing on the shore, how fast does it actually look like the boat's moving? If we're standing on the shore, does it look like it's moving 9, 6, 15? None of the above. So if we're observing the boat from here, if we're observing the boat from here, the boat's not just moving 9 meters per second, it's not just moving 6 meters per second, it's moving the vector sum of both of those values. So just like we had above here, I would add my vectors tip to tail, 9, 6, and the way my person on the shore would observe it is moving at whatever this value is. So 81 plus 36 and the square root of that value, or 10.8 meters per second. Because 9 squared plus 6 squared equals c squared. C turns out to be 9.8. So when we work with these problems where we're moving in 2 dimensions, vector addition can give us the total velocity, but we still have to also look at this in terms of individual problems. One of the students I had a few years ago said that he was going to call this the property of dimensional isolation. And what he meant by the property of dimensional isolation was that any velocity or any motion that he has in one dimension doesn't change motion or velocity in the opposite dimension, the other dimension. So when we look at this boat moving across at 9 meters per second, that doesn't change how the river flows. Likewise, the river flowing doesn't change the ability of the person paddling to row at 9 meters per second. So if I identify my variables in the x and y dimension here, note for this problem, there's no acceleration. So I don't have to worry about an acceleration here. I can just have velocity in the x, change in position, and time. And here, velocity in the y, change in position in the y, and time. The only value that's going to be the same between these is time. Good with that idea? Because time moves forward regardless of what we're doing. Looking at the scenario we've got drawn out here, what variables can you identify right now? Which one? Is how much? Okay. What else? Sorry, I can't hear you. Okay. 9 meters per second. And anything else? All right, so 40 meters. So now we can use the simple equation v equals delta x over t in order to figure out how long it takes the boat to travel from one side to the other. So vy equals delta y over t, 9 equals 40 over t, 40 over 9. I get that it's in the water for 4.4 seconds. Now, because we said that time was the same in both dimensions, that means that this is also 4.4 seconds. And then our boat winds up, times 6, 26.7 meters downriver. Questions about how we found that? Okay, so if the person paddling the boat doesn't want to wind up that far downriver, what are they probably going to do? Row at an angle up. Okay, so we're going to angle our boat slightly across the river this time. So instead of this 9 meters per second, we're going to angle here at 45 degrees. He's still paddling at 9 meters per second, but now part of his velocity is directed across the river, part of it is directed upriver. How do I go about figuring out how much each is? Yeah, sine. Yep, we can use sine, cosine to break this 9 down into components, the opposite of what we were doing here. Here we were using finding an angle based on page. Here we were using an angle based on, or finding an angle based on the components. Now we're going to find the components based on the angle and hypotenuse. So redrawing this, 9 meters per second, 45 degrees. Uh, 9 sine of 45, 6.4 meters per second. And 9 cosine of 45, oh look, it's the same thing. All right. Now we've got a boat that's angling upriver. What would I have to do to go about figuring out how far downriver or upriver now this boat's going to land? What would I have to do next? All right, I like that answer. So I've got a boat that's going upriver at 6.4 and a river that's coming down at 6. So in my x dimension, my velocity in the x dimension is how much? So I'm going to call it negative 0.4 since I've been treating downstream as positive so far. Anyone not sure how we got 0.4? Yeah, I can do that. Anyone not sure how we got 0.4? Or why we got 0.4? Yep. So it's just the combination of the two. We're just subtracting off one value from the other to find what the resultant velocity is. Delta x, t, and in the y dimension, velocity in the y, delta y, t. What other variables do I know in this scenario? Velocity in the y, how much? All right. What else do I know? Time's the same. And I do know this one as well because my river is not changing. It's still 40 meters across. So just like before, I'm going to find v equals delta y over t. 6.4 equals 40 over t. 40 divided by 6.4 gives me 6.3 seconds. Meaning that this must also be 6.3 seconds because time is the same in both dimensions. And lastly, negative 0.4 equals delta x over 6.3. I get negative 2.5 meters. Questions on this one? Yeah. Okay. River's flowing down at 6 meters per second. Are you good with how we got negative 6.4 here? Well, it's got to be negative because if this is positive, this is going in the opposite direction. So this has to be a negative value. Okay? So when we look at our velocities in the x dimension, since these are opposite directions, this one has to be negative. So when we add those velocities together, we wind up with negative 0.4. So graphically adding them, we would have looked at something like 6 meters per second from the river, and then going back the other direction, 6.4 from the guy actually paddling, leaving us with just this smidgen of value left here at 0.4. And because it's acting in the left direction, negative 0.4. Good? Anybody else? All right, then let's talk about a different kind of scenario. Rather than a boat and a river, we're going to talk planes. So a few years ago, I actually had a student who went on to get his pilot's license. And one of the things he said that physics was actually useful for him was passing some of his pilot's tests. Because in addition to actually being able to navigate a plane, one of the things they had to do in aviation was be able to add vectors for his plane's velocity and the wind heading in order to figure out how to compensate for wind headings. Now, yes, in a plane, there's all sorts of instrumentation that does this. However, they were required to be able to do it by hand in case the instrumentation went out. So, if we've got a map, we'll put Fargo here. They're roughly the same latitude, Bozeman, Montana. Okay? If it's roughly the same latitude, what direction would you have to fly your plane? Rather directly. If you're to go from Fargo to Bozeman. West. And so for the purpose of this, let's say that a plane, specific plane we're looking at is capable of flying at 500 kilometers per hour. The plane flies at 500 kilometers per hour. However, what are the chances that we actually have no wind in North Dakota? Basically zero. Okay, so in that flight, it flies into a wind. The plane flies in a wind of 75 kilometers per hour. That's going, let's say, just 45 degrees south of east. Meaning that if I were to draw the vector for the wind, it would look something like this. 75, 45 degrees. So our question here could be something to the effect of, how does the pilot have to adjust the heading of the plane, meaning where are they going to point the nose of the plane in order to account for this wind? Because if the pilot doesn't account for the wind, where's the pilot going to wind up when they fly straight west? Okay, no, not that far south. But I was going to say like Wyoming, maybe Yellowstone probably. Just around this location, not where the actual landing strip is. So at what heading or what angle should the pilot fly? Take a second. Based on the boat problems we just did, see if you can figure out how you should start this one. All right, what did you guys do to start this problem? What's the first thing you did? Okay, so you broke this down into components. So 75 sine 45 gives me 53 and 53. Anytime you've got a vector that is not just in the x and y axis, first thing you should do is just break it down into components. Makes everything easier. Okay, I'm still going to use the DICE's steps. Draw, identify, convert, equation, solve. I'm going to start out by drawing because graphically laying out vector addition helps me picture what do I actually have to do with the numbers. So I know that my plane's going to do something like this, 500. I know I've got to angle it above the x-axis because otherwise I wind up south in like Wyoming or something. Then I'm going to draw my other vector here, tip to tail, meaning that the arrow is the tip and the tail is this back end. And I'm going to draw something like this. I know I'm trying to get them to line up. So these should be roughly here. Now I know that I can't draw to scale, but this piece here and this piece here are both 53 because we just found that value. At this point, I've now created a new right triangle. My new right triangle is this one here. I can now use that in order to figure out what is my heading that I need my plane to fly at. So I'm going to use tangent of my angle, or sorry, not tangent. I want sine of my angle. Sine of my angle is equal to opposite, which is 53, over 500. Inverse sine of 53 over 500. I get 6.1 degrees. So my pilot would have to point the plane 6.1 degrees this way. How can I define this? Well, if I know that the plane's going west and this is north, I could say 6.1 degrees north of west as my heading for the plane. Next question, how fast would somebody on the ground see the plane moving? Well, if this was my component vectors, these two, my resultant vector, or how fast the plane looks like it's moving, is just this segment. So to find that, I can just use some additional triangular geometry to figure it out. I know I've got a hypotenuse, I know I've got a singular side. What do you want to use to figure out this remaining side? Pythagorean theorem works for me. 500 squared equals 53 squared plus b squared minus 53 squared, and the square root of that value is 497. So would an observer see the plane flying at 497? Why not? You're on the right track, but it's not a full 75. The 53. Yeah, we've still got to overcome that 53. So minus an additional 53, they would observe 444 kilometers per hour, which would be represented by this piece here. That's what we would see, is we would see the plane flying straight across at 444 kilometers per hour. Where are you? Oh, yeah, 497?
Yeah.
Is this? Yes. Anybody else? Okay. Let's try a couple more of these. Just to make sure we've got a hang of them. Actually, you know what? Let's go back to that boat. So keeping our displacement of 40 meters across the river, and our river's still 6 meters per second, and our boat paddler can still travel at 9 meters per second. Last time we looked at this example, we had him going at 45 degrees, and he wound up being upstream by about 2.5 meters. This time, we want to know what angle did he actually have to point the boat at in order to land directly across the river. So at what angle should the boat point to travel straight across the river? So I'm just going to erase or scribble this piece out because that was from an old example. Take a moment, see if you can work through this one. So as I suggested, the first thing I would do would be add these vectors graphically. So I've got this piece going up here at 9 meters per second. And I've got the water pulling back at 6 meters per second. Now I'm going to stop these so that they're even, because the goal of this problem is to find what angle the boat should travel at in order to go straight across the river. We want to go straight across the river, meaning that all I need is whatever angle this is going to be. So a straightforward problem. I'm just going to take the sine of my angle equals 6 over 9, opposite over hypotenuse, inverse sine of 6 over 9, and I get 42 degrees. How many people had 42 degrees? How many people had this drawn? Okay. Anybody draw the 6 going over further? Okay, good. All right, so all we had to do was recognize that in order for the boat to compensate for the river, it just needs to make sure that it pushes out further past it, so that this component is also 6. Once we've got that, we've got our angle built into our triangle that we've already drawn. All right. Questions on this one? So for the last